work with embedded control systems. I do work with diagnosing control systems. My background's BS in electrical engineering, and just across the bridge, I've got a master's degree in materials engineering over at Research Building 2. I've worked with programming and electronics for many, many years, and it's one of the things that I do for fun.
Oh, I'm sure does.
Okay, well, as we said, Shane is going to talk about sensors and with emphasis on demonstrations. And let's go with that.
Okay. Again, I'm Shane Trent, and I'm hoping to be able to give you a little useful information about sensors. Feel free to jump in at any time and ask a question. Struggle with how much is going to be things you already know versus I'm skipping stuff that I don't think about anymore. So feel free to jump in and give some guidance or ask questions. Starting out, I'm going to be referencing most of what I'm talking about to the Arduino Uno. That just seems to be the least common denominator, that if you're working on one of the other platforms, one of the Mega or Leonardo, that, or Raspberry Pi for that matter, a lot of the same signal conditioning fundamentals will apply, but you may have to change references to port numbers or references. The Arduino Uno, most of them we're talking about sensors. Usually you're talking about using an analog input channel to read an analog voltage. The Uno has 6 channels. All of them are 10-bit, which means that you get one part in 1024, which gives you a resolution of about a little better than 5 millivolts with the standard voltage reference. So it's a huge step up from an 8-bit reference. Again, the default analog reference is the 5 volts. That most of the time you won't care about it. That'll just be what goes. One of the things to know is that there are other reference options, internal and external. The internal is a 1.1 volt reference. So if all of a sudden your numbers are seeming off scale, check and make sure that there's not a piece of code in there somewhere that says analog reference internal. Myself, I got bit in a project when I could not figure out why my signal conditioning was going all wonky. My channels were all over the place. I was getting high values, low values. Turned out that a piece of code that I'd copied and pasted from another project changed the analog reference to external, and I had nothing connected to external. So it was out there floating in the wind, and just depending on how close my hand may happen to be to that pin, the values went all over the place. It took me a whole evening of gnashing of teeth to provide it. And
that's part of the job.
It was very educational. Now I look for it. Yes, Paul?
Do you know if the default reference says it's 5 volts? Is it V in or is it 5 volts? If you only give it 4.5 volts, is it 5 volts?
I believe that it's 5. It's 5. That, well, so if you feed in 4.4, it doesn't have a charge pump to generate 5.
Well, it's the supply voltage.
So
right?
it is
V in.
But
yes.
no, because I'm actually dependent on that, and I'm doing measurements relative to something, and my reference is 5 volts, even if my supply voltage going in V in is 9 volts.
What if your voltage going in is?
I think Paul's was V in for the chip, VCC for the Arduino chip for the 328, not for the Arduino board.
It's relative to the, it's the power supply voltage.
For the chip.
It's VCC, isn't it?
Yes.
Right. Sorry, I misunderstood your question.
Quite all right. And again, I've never used the external voltage reference, but I could imagine circumstances where you're exciting an external bridge and you want to match your reference voltage. You may be, driving a bridge and looking at a 500 millivolt signal, so you want a 500 millivolt reference for full scale. My keys for success for working with sensors. These are things that I keep going back to when I feel like I'm having an issue with a project, or I'm wanting to learn to use a new sensor. Go find example code. One of the most powerful things that the Arduino has going for it is a fantastic library of code that's been tested, it's worked, it's well commented, it's well discussed. So I always go back and find an example there. If you're looking for something you don't have an existing example, Google it. The Arduino is so popular that you can find example code for most everything out there. That if you can't find it for something out there, if you check the discussion boards and if you participate, there will be someone who's excited to help work with you and help you build one. One of the things I like to tell people to be sure is save your code often and use revision numbers. That if you're making progress fast and furious and you're saving over and over and all of a sudden something breaks, if you don't have previous revisions that you can go back to that you know work, you can start tripping over your own feet trying to backtrack out and figure out what caused the glitch. Dropbox is awesome. I actually had a computer out of my garage fail 2 days ago when I was doing some demo code for this, and I hadn't given a second thought about backing it up. I haven't moved anything other than Dropbox in years, and sure enough, even though that computer was dead as a doornail, all the code was on my other computers, and as soon as I fired my laptop, it came there from Dropbox.
The Dropbox is like box.net, cloud.
Yeah, cloud server. Use some sort of cloud service for synchronizing your files. It's too easy not to use. I mean, it's free for 2 gig. I know other services offer 5 or 7.
I got 3 and that was free. There's various things you can do to bump up the amount
Yeah,
of free.
upload photos, upload videos, invite friends.
Google also offers similar services.
Google Drive. Yeah, Google Drive is awesome, but use some sort of cloud service. It's just too easy to have it synchronize and back up your code. There's my
Use GitHub, and then you've got a.
Somebody needs to give a presentation on GitHub.
Yeah, I use it all the time.
But I have yet to sync a library from GitHub. I've downloaded many, but syncing one using
You mean
the clone.
putting code up?
No, what do they call it? Cloning.
Oh, the clone. Well, that's how you pull the code down.
No, I pull the
to your-
zip file and then compress.
Oh, you do it that way.
Yeah, that's what I'm saying.
No,
Very-
you do git clone and then,
Let's see, another thing, check your analog reference. Another thing when you're working with sensors is watch for sensors that you're powering from your VN to the board, that because your VN may fluctuate, and when that fluctuates, if you're using a pull-up or if you're driving a bridge or if you're using a voltage reference or a voltage divider off of that, that can fluctuate even though your voltage reference doesn't. So you may be thinking your signal's fluctuating when it's actually your power supply or the battery that you're connected to. One of the things, one of the first things to familiarize yourself with when you're using the analog inputs on the Arduino is go to the Arduino site, check the references out, and look at the math functions. There are some very cool and very handy math functions. I believe the most handy is the map function. That I didn't go check the reference the first several times. I was reading signals in and doing my own signal conditioning, so I built the map function myself so I could scale whatever I wanted, wherever I wanted it. And then to find that was one line that already existed, that not reading the documentation carries its own punishment.
You can do that with 2 characters.
Well, the thing
3.
I love
I'm
about...
sorry, 3. Greater than 2.
Oh, well, the thing that I like about this is to say you want it to go up when you twist the knob the other way, you just reverse these numbers.
Reverse it, yeah.
Changes the function. If you decide, oh, I only want to use the bottom third of the scale, you can change it to the bottom third of the scale and map it to whatever output you want. It gives you a lot of room to experiment without breaking things, versus if you're trying to do the scaling yourself. It's a lot more challenging, but there's min, max functions. I can't remember if it's confined. There's one that makes sure it limits between a high and low value. Hardware success when you're messing with sensors. You will cross wires. You will reverse VCC and ground. You will let the smoke out. It's been a week and a half since I killed the CPU. Hopefully it'll be 2.5 weeks this time next week. I recommend, if having an Arduino with a socket for the 328 chip, if you can get it, go on Amazon. I'll have a link. I'll send a link out with some of my notes from the presentation, and I've got links there for sources where, this is the Amazon place to go get a Uno with the 328 chip. Here's a place you can buy 328 chips. The biggest challenge is using Paul's information from his presentation last week, and you can use your existing Arduino to burn the bootloader on to 328p chips. You can buy the chips, I think, starting in singles for like $2.40 from Mauser. So when you smoke a chip, it's not so much that you're out $2.40 instead of $24, but it's that you can pop it out, pop it in, and go back to work, and you don't have to wait for FedEx tomorrow or Monday. Heaven forbid it happens on a Saturday. Use your multimeter when sometimes when you think a sensor's doing a crazy thing or your software's doing something crazy. Break out your multimeter, check it on the pin. Lots of times I've seen a resistor fail and you don't know it's failed, so you think you've got a voltage divider going on and you don't. Try a different pin. I have burned out pins on a specific chip because I momentarily lost my ground and I was driving 14 volts into a 5-volt pin and no smoke came out, but it's giving me bogus numbers. You may be able to move just down another channel, and when you do it, make note that that chip's in need of replacement, but at least you can continue developing. And if that doesn't fix it, it measures the correct voltage on the pin, but you're getting bogus values, you can try another chip. These are things that can help you not hit a roadblock when you're working on something, you know, yourself, the evening, the weekend, whatever. As far as conditioning the signals for running to the analog ports, the biggest rule is don't let the signal get over 5 volts. You're not guaranteed to let the smoke out. In fact, if you have a large enough input resistance, generally you won't kill the chip, but you also really can't say anything qualitative about the values that you're reading off the A to D converter. So you want to use a voltage divider for signals that you have that are over 5 volts. So if you're monitoring the battery voltage in your car, my favorite combination is a 4-to-1 voltage divider, so the 5-volt input gives you up to 20 volts on the battery, and you're good there with a 1K and a 3K. If you've got a low voltage, you can use a buffer. I've got a note here about Instrumentation Amps. They're basically a very fancy op amp. You can hook those up to a floating source or a differential source, and it changes a differential signal into a single-ended, which means you could be measuring the current across a high-side resistor and then measure that with an analog input, and you can do that without worrying about what voltage the resistor, the resistor may be at 14 volts in an automotive application, and you're wanting to measure a 300 millivolt signal. Well, the instrumentation amp will let you take that signal from that high side voltage and reference it to ground. Any Google search will point you in the direction of half a dozen. If you're trying to measure something specific, there are lots of options for specialized chips. I mentioned measuring current. You can get specialized chips from several different companies that are made just to set on the high side and take a low voltage from across a current shunt and turn that into a workable voltage. You can also buy things off the shelf. On the left here, I believe that's from Spark Fun. That is a current shunt with the built-in resistors and everything already set for measuring 180 amps. So I suspect looks like a 1 milliohm resistor on this side. I suspect the flip side has another milliohm, so that's a 0.5 milliohm current shunt. And I suspect there's a chip on the other side that provides amplification. The one on the right is a Thermocouple chip from Adafruit. I believe it's $18 or so, but it includes the cold junction compensation and the signal conditioning and everything you need to drop onto a breadboard, connect a K-type thermocouple, and make thermocouple readings with your Arduino without you having to design the circuit or solder something up or write the code or build the drivers. SparkFun and Adafruit are both great resources when you're looking for either signal conditioning or specific chips or outputs or inputs. Adafruit in particular has some excellent tutorials on how to use a fingerprint sensor, how to use infrared sensors, how to use any number of things. They've got great discussions. They and SparkFun also lean towards open source. So most of those you can go and they will give you the source code for all the demos, so you just download it and run it. Most of them, you can also download the actual board files, usually in Eagle, so you can have your own board that's fabbed, or if you want to say, hey, I want to take this design, drop it onto a Arduino or a 328p version that you're wanting to make for yourself, you can grab that, know it works, drop it in, and integrate it and go from there. Analog sensors, there are just so many that fall into place. First and foremost, the first one almost everybody uses on an Arduino is potentiometer, just because you can reach down and grab it and see that it's doing something. You can use it to change timing parameters in software, whether you're pulse width modulating or whether you're doing timing issues. All kinds of temperature sensors, temperature sensors, photodiodes, pressure, strain, light. One of the things, if you're doing a lot of signal conditioning, I recommend checking out Omega. They make a slew of temperature, pressure, strain gauges. They've got free handbooks that you can download PDFs. They've got free handbooks that they will send you by the crate. Fantastic discussions on strain gauges, on temperature sensors, PID control, tuning PIDs. They're just a plethora. One of the things that the Arduino brings is the chance to build what you want. If you can't find a sensor that does exactly what you want, one of the examples that I'll talk more about later is I was working on a project using 3D LCD glasses, the shutter glasses for viewing TV in 3D. I was trying to recreate the drive signal to drive a pair of Sony 3D glasses, and I could get them to fire, but I was not able to tell from looking at what was going on, so I needed a sensor that would let me see what was going on with the transmission of the actual LCD frame. So I took a photodiode, LEDs, clothespin, and wired up a clamp that I could put straight onto the LCD glasses, hook it up to the scope, and I could see exactly what was going on with the phase relationship between my IR drive signals and the duty cycles I was seeing on the actual shutters. All parts I happened to have at the house. It was very fun. When I saw those curves for the first time on the oscilloscope, I was cheering. Digital sensors. These would not use necessarily the analog inputs. I believe it's the SPI port that actually sits on top of the high number analog input channels. Is that SPI or is that I2C?
That's I2C.
I2C. Because I know that there's a very cool little teeny tiny circuit board that you can get that you can pop on the end of the analog inputs and use a Wii nunchuck remote with the switches and the 4-direction hat switch and read that directly into the Arduino and use it for control, remote control. And again, the board's like $2 from SparkFun, and all the code is done, canned, examples there, so just fire it up and use it. Again, we come back to find an example that if you need something, go and look. Someone has used it or something like it. If you can't find it, then study the data sheet, see how complicated it is. Usually if you go slow enough and look at the signal maps and transitions, you can figure out how to talk to the chip and run it. The fallback from that is find a similar chip and see if you can find an example that someone has already done. And past that, hit the discussion boards at Adafruit, at SparkFun, at Arduino, and someone will have some suggestion to get you started in the right direction. I've got sensors hooked up on the board.
That's the one I was using, that temperature sensor.
The LM34?
No, the TS18
Oh, the digital one.
B20.
Very, very popular digital temperature sensor. I think it can be configured from, I can't remember if it's 9 bits or 8 bits all the way up to 11 bits with some particular hand waving. What I really like about it is that you can use it on multiple drops. You can have multiple sensors on it, and
right.
Each individual sensor also has a unique ID. So if a sensor is pulled out and replaced, it knows that the sensor's been pulled out and replaced. If a sensor dies, it can tell you which sensor died.
It uses the one wire library.
That all the ones on the top are analog. But I've got a potentiometer on here, a thermistor, an LM34, a cadmium sulfide cell, and a barometric pressure sensor, which I just threw in there because barometric pressure sounds interesting, but when you're, I was telling Paul, when you're looking at barometric pressure sensor, you hook it up and you get a number and then it just sits there and doesn't change. I could have just typed the number and it's going to look the same. you'd have to watch it for days and graph it to see it, but.
Wait for a hurricane?
Yeah.
Any old rain shower will
But,
cause the barometric pressure to go down.
Well, if you get enough temperature fluctuation, you'll see it swing a little bit.
What will you address when I would use a analog as opposed, I would always pick an analog temperature as
Analog is
opposed
nice
to digital.
just because you can put your multimeter on it. You can verify that it's really doing this. I tend to go with the analog when I can lay my hands on it, when it's something that lends itself. But say if you want to, you're measuring, you're doing brewing or something, and you're wanting to measure the temperature in a tank at 10 different points. Well, you're out of analog channels until you start adding some external switching and external multiplexing. But the Dallas one wire, you could hook up 10 of those, no sweat, read them in on one pin. So usually the circumstances will steer you in one way or the other. There are a lot of modern chips that only exist in a digital format. And one of the nice things about the digital format, like something like the LM34, those are laser trimmed at the factory for accuracy. The 34 is the Fahrenheit flavor. It's generally spec'd at plus or minus 0.4 degrees Fahrenheit through laser trimming. But a lot of the newer sensors, particularly if you're looking at a strain gauge or if you're looking at something that like a light sensor, that those will be calibrated and the calibration is stored in the device. And that's not really feasible with the analog sensors in most cases. One of the things that was the rage 10 years ago was TEDS sensors, transducer electronic data sheets. So there was actually calibration data embedded in the device. It's big in test and measurement for tracing, so that if you have a sensor that needs to be replaced, it's time for it to go for calibration, you pop in a replacement, the system recognizes that it's been replaced, it reads the calibration data off of it, it knows how to normalize the data, and you've gone from, say, plus or minus 3% to plus or minus 0.5% error by using a digital sensor. So there are a lot of them out there, but the beauty of it is they're really adventurous, really cool, really smart people who will go out there and write the drivers and give you example code. Like for the one-wire sensor, the only thing I did was drop the library in, restarted the Arduino, put it on the pin it told me to put it on, and it read the
I
note.
think you need like one resistor with that.
A 4.7K pull-up.
Yeah.
There's even, you still need the resistor. You don't have to have a power supply. You can do it over 2 wires, but I went ahead and did it over 3. But it's fall off a log simple if you can find the example code that someone else has done. And there are people who can attack things like that, and with no documentation that can reverse engineer protocol and put together a driver that'll work. It's really amazing some of the things that you can find, particularly on Adafruit. I've been really impressed with the stuff that they've put together. But I'm going to go ahead and go past. We'll back up in a minute, switch over to the overhead, and do the demo. Oh, here are some of the resources. So this is where I was going to stop. Again, Adafruit, SparkFun, Arduino, the reference information at Arduino. That I can't tell you how many times I go back there and study a function to really understand, is there a better way to do what I'm trying to do. Pololu out of Las Vegas, they're less open source, but I actually go there lots of times to look at their designs. Anytime I want to know what the lowest RDS MOSFET I can get in an SO8 footprint, I don't hit the data sheets and browse through Mouse or DigiKey. I go to Pololu, I look up their motor control boards and whatever esoteric chip they've got on that. That is the highest performance SO8 MOSFET you can get in that form factor. I also learned a really cool trick from them about using an InFET pull down wired up to the incoming voltage. So in essence, if you hook the voltage up backwards, you have a backwards diode and an unbiased FET disconnecting the power from the circuit. You connect it correctly. The incoming VS pulls the gate of the InFET all the way up, saturates it, the drop on the FET goes to practically 0. So it's like having a reverse diode protection without the forward drop of the diode. It is so cool. Well, the thing is that you know that they have had so many returns from, well, I just connected it backwards for a second before the smoke came out.
What is it, the BS 120, what's the one used for level translators so often?
I have no idea. What I did was I went and looked for the lowest RDS I could find in a TO92 package, and I found one that was rated, I believe, for 0.75 amps in a TO92 with the logic level, and I've just been sticking that on everything. It's just really handy. I actually stuck it on a voltage converter for my father-in-law. He has a Studebaker with a 6-volt positive ground electrical system, so he can't run his GPS and he can't charge his cell phone. So I went to Pololu. I bought one of their teeny tiny, just postage stamp size voltage converters that will take a 6-volt signal, has an adjustable output. I dialed it to 13 or 13.8 volts and shrink wrapped the whole thing, and I put one of the reverse FETs on there for him so I knew he couldn't hook it up backwards, and gave it to him, and that he said, well, it didn't quite work. And like when he handed it back to me, it was like this charred, smoky remains of wire drooping down. I thought, oh man, I don't know what I did. I must have connected something backwards, and I'm doing the post analysis on my workbench. And I'm hooking it up, and I'm not measuring any shorts anywhere. And I thought, well, that's odd. And I hook up the inputs, and I measure the outputs. It's like, holy cow, it's alive. It turns out what he'd done was use a metal shell cigarette lighter outlet. So when he connected the ground of the battery ground to the shell of the electrical outlet that was mounted in the dash, which is connected to chassis of a positive ground 6-volt system, it was a dead short through the body, through the wire. It just took a second. I really complimented him on the quality of his grounds on the car. They had to be excellent because there was very little voltage drop until you hit that wire. The 12-gauge wire just heated up and the insulation fell off of it. So I went back for the next install and helped him. And we wrapped that same metal outlet in 2 layers of electrical tape before we eased it back into the dash. And to this day, he's got the only Studebaker at the show that he can plug his cell phone and GPS into the cigarette lighter out in the dash. He loves to show his friends because it still looks factory. But that backwards FET saved me on that project. Any other questions?
I got to learn more about that.
It is a very cool trick.
Draw the schematic later.
Okay.
After you're done.
Yeah,
I want to see.
Yeah,
Okay.
do that.
Well, I'll do that. And there's one other trick. Has anyone ever heard of a G node? JEE. European guy. He's making Arduino compatible-ish stuff, but using the AT Tinies, and he's doing it in a yay big form factor. And he's using, I believe, the AT Tiny 84s, and makes it with 4 ports. But he makes 4 little ports with some number of header pins, and each one accepts a different little device. The email I'll send out has a reference that will mention him. But one of the things that I saw was a way to use a voltage divider to measure battery voltage, and he hangs a PFET off of the top of it. So it's disconnected, it only connects through the PFET, and drives it with the capacitor in series with the gate. So when he hits it with a pulse for 2 milliseconds, the PFET turns on while the capacitor is charging, and he can turn the PFET on, go measure the voltage with the analog input, turn it off, it dissipates, and then it sits there disconnected with no voltage divider drop across the battery until you want to take a measurement. It was very cool. I had to read it 3 or 4 times before I understood it, but it's like, wow, I owe somebody a cup of coffee for that. That's very nifty. But we'll jump into the demo, and then I'll show you what I'm talking about with the low side polarity protection PFET. I think I'm done here. How do I switch over to the...
There's a button on the front there.
Here.
Just a little panel there.
That little panel.
Okay.
It says dock cam.
Laptop dot cam?
Dot cam, yeah, something like that.
There we go.
Now we will wish we had a higher frame rate.
No computer. Okay.
Not the overhead.
If I disconnect this off, you can't see the screen.
Oh, so you got an Adafruit board.
Yes. Yeah, the little laser cut.
I got
thing.
one of those from my Beagle Bone. Very good.
it's embarrassing how much money I send to Spark Fun, Pololu, and Adafruit. I mean, I've got an ongoing wish list for all of them.
Keeps it in the country, it's good.
Absolutely, and you got to support open source. I mean, so many things that those guys could keep close to the vest and keep to themselves. Well, one of the cool things is, well, you guys are going to miss it. What I was going to show you is I'm pleased that all my demos here, all I'm doing is pulling up the standard analog in, serial out example that comes with the Arduino environment. That is my go-to whenever I'm trying to test any analog something, because it lets you read the analog information, lets you do signal conditioning on it, and spits it out the serial port so that you can see what is going on with your signal. You can twist the knob. This one, do I have the, yeah, I do have the LED hooked up on this one. So I'm going to program this one, and this will be the pot. Yeah, I apologize. I'll have to switch it back to the screen to.
You could just toggle it right there. Any buttons. So we can
Let's
see
see
what
what
you
comes
see.
back. Compiling.
So what are you doing right now?
What it's going to do is read.
No, on your
It's
laptop,
compiling.
what are you,
Oh,
okay.
it's compiling slowly for some reason. I don't know.
Yeah, it's Arduino, or the Arduino environment.
Well, usually it's faster than this. Actually,
Screen recorder, maybe?
You know, there's a really good make-file out there for Arduino.
Well, I was going to say that the only reason I don't use AVR Dude is that I do not have the chops to can my own make file and issue it from a command line.
Well, there's one you can get, actually, Pete, and I sent a bug off to him, which he's going to have fix in the next version.
We'd have that on a link on a resource sub-link page or something. I think that'd be handy.
Speak HTML?
I know it when I see it. That's about it.
It's actually quite easy to use. Their make-file works, and I almost universally use that now.
That well, the few times I've gone and used the AVR Studio, it's been, what? You mean I've got to do something else? I've compiled it, now what do I have to do? Where I've gotten lazy with the Arduino, just hitting and have it do everything.
With this
for-
make-file, you can compile it, you can burn it to your board, you can clean up your directory tree, you can do all sorts of stuff with it.
All right,
It's really cool.
last month, you had code, I learned about Sketch and all that stuff, and I thought that you wrote the code in the IDE, the Arduino IDE,
Yeah.
and it went to the board, and it was all over.
It is, that's what it is.
So what is he doing?
He's waiting, I don't know why it's taking so long.
Yeah,
Yeah,
but
I'm-
didn't you do that
I feel
when
like
he
I'm
made
in
this
some
thing?
conflict
You
with the.
can't, you simply, you can only see one thing at a time. You can either see the screen of his laptop or the projector.
Yeah, but I thought he'd written the code for this last month, and,
No, I didn't write anything ever. I'm just pulling up an example, but I'm getting some conflict
oh, okay.
because when I'm
All right.
opening the IDE, I'm seeing the screen capture software going in the background. It's doing the.
That's
Run it. It assumes that you have your analog sensor connected to analog input A0. You've got I put an LED on pin 9, but I'm not really using it. There we go. That's moving a little better.
How big of a sketch is this?
It's tiny. Let me kill the.
yeah, you should turn that
Let
off.
me close the VLC media button and see if that.
Might also.
Oh, that seemed to.
Nope.
Oh,
No,
commate
that
not
died.
found. Let's see.
Musical chairs on the COM port.
Yeah, it's.
When this is all finished, though, he would take this and burn it to the board, and then we'd have to do this again?
He is about to burn it to the board, and then he wouldn't have to do it again. Every
Okay.
time the
There we go.
port
That's how
is
long it
powered
should
up,
take.
it would run that
There,
code.
that's,
Okay.
that's more like it.
That's way more like it. It was confused. Okay. And what I can show you, pull up the serial monitor, make sure it's set for 9600. Now, it's reading my analog input, and you can't really see the little red LED, but if I hold it up, you can. So it's reading, and one of the neat things using that map command, I've got it set up to increase the brightness as I rotate it clockwise, just because that's how I want it to be. I actually had to move the wires to make it do that, but that's only because I had to do that in the stock code.
I'm always getting the populated backwards.
But, well, that's the nice
You
thing.
turn up and the voltage goes down.
That's when you put the, change the level from volume to attenuation. Oh, sure.
I was just want to make sure so that the sensor you said was the 10, so that can go from 0 to...
Yes, yeah, I'll show that, that should go to max it out. The PWM, the PWM accept the analog outputs, which are, I always use 9, 10, 11, just because they're 3 pins in a row, for RGB type stuff. Those take an 8-bit value, they modulated, I believe, around 400 hertz, and they do a nice square duty cycle.
So it's pulse width modulation?
Correct.
And is there ever an issue with the fact that your analog sensor has more granularity than your analog?
The problem is actually the reverse.
Okay.
That we have extra resolution, so we will be able to make teeny tiny changes to our input that'll have no impact on the output.
Right.
It'll sit there. You have a little bit of quantization error.
Okay.
It gets uglier when you go the other way around. So if you've got a signal that only goes up to, like that's for a 5-volt signal. If you have a signal that only goes up to 500 millivolts, a half a volt, then your maximum output would be 102. Well, you're mapping 102 to 255, and then what you're going to have is you make a small jump and the output jumps 3 notches, or the output jumps 4 notches. So it starts getting chunky.
And I was noticing on Adafruit and SparkFun that some of the sensors, instead of being 5-volt sensors, were 3.3 volts.
Yeah.
3.3, you get used to it, accept it. I mean, you know, we will all warn 5 volt. And
The
all of our
Raspberry
5-volt
Pi
accessories.
is 3.3
Okay.
volts.
The-
All right, you put 5 volts in an RPI and you blow it out.
The Arduino.
Same thing with a BeagleBone. You do not want to use 5 volts around those
Does
things.
that mean I wouldn't get that full 2 to the 10th granularity
Yes, at
on a
3.3
3.3 volt sensor?
Yes.
Oh, that's not good. And
And you are only talking about
Unless I
the
scale it somehow?
GPIO pins. You're not talking about my power supply.
That's
What-
right.
What they're doing
Okay.
is, if you could run a 328p, I believe all the way down to 2.2 volts,
Oh,
something like that.
VCC could be.
So if you run VCC down to 3.3 volts, this 1023 will equate to 3.3 volts, because that's how the reference comes out. But
At 3.3 volts, it will only run reliably at 8 megahertz.
yes, yeah, you have to start dialing the voltage down once you go below 3 or 3.3 volts. Yes, sir.
Some Arduino clone boards have a switch to put it down to 3.3 volts.
Sweet.
Just switch the whole CPU, everything down to 3.3 volts.
I know the new Arduino Leonardo is 3.3 if I'm not mistaken. And I believe the,
That's using a Cortex processor now. It's actually an
no,
Arduino.
that's the Explorer.
Oh, Explorer.
Is it Arduino Explorer? What's the one that's shaped like a gamepad? Isn't that the one that
It's
uses
not
the
Leonardo.
No, the Leonardo uses the, not 328p,
It's
but
the new one. There's a new,
Yeah, I
the
think it's
Duo or not the
Explorer?
Duo. I forget
We
what
have the
Duo.
technology.
Yeah, yeah, it has a Cortex.
Oh, see it. So some mapping. Explorer, that's the one I was thinking of right there.
I don't think it's that one. There's another one. Yeah, the Arduino was invented in Italy. That's what the.
Okay, no, the Leonardo and the Explorer both use the 3.3, 32U4, so that's not the one.
No.
Okay. There we go. The one with the big chip.
That looks like it.
And the problem with that one is not all your shields will work, right? If you have
That's-
5.5 volt shield.
That's right. And if you notice there's more space between some of the sockets on there, so they're not 100% incompatible.
So if I haven't invested a lot of money in shield yet, should I go with this route?
Well, they're saying that this is going to be the direction they're going in for all future stuff.
Wow.
And shields, there's a pin somewhere up beyond 10, 11, 12, 13, which tells the shield whether it's a 5 volt or a 3.3 volt. And so if you're developing new shields, you're supposed to use these pins to properly select between the voltages. But all the old shields don't have that.
When you say shields, pardon me, what are we talking about?
Daughter board.
Shields are daughter boards that plug onto the,
Oh, okay, oh, all right.
onto the processor.
It's one of these things, sketch instead of code, yeah.
Right.
Okay.
But yes, back to the 3.3 versus the, did that answer?
It did, thank you. Yeah, that's good.
So is there a map line in the code in the standard
Yes.
login?
Yes, there
Serial
is.
out?
That is doing the magic for us right there.
Okay.
That is, again, just the handiest thing. And I was saying, if you want the knob, when you turn the knob like this, turning it clockwise makes it brighter. Put the 255 here and the 0 there. It'll be brightest at 0, and it'll get dimmer as you crank it up. And you can also map it to a range. I have to put a caveat there. When you're mapping a sub-range, you could say, I want to map 0 to 512 to full-scale output, to say you're using a sensor that has a maximum output of 2.5 volts. But it gets a little hinky when you do that and then you exceed this number, because it starts pushing this number past 255. And then when you run a number past 255 into an argument that's expecting a maximum of 255, then it starts to ramp, and you go from something that's supposed to be fully on, it goes to off, and then starts acting funny. So if you see things start going fun with your code, that's when you bring up the COM port. And if you look through my code, you will find in all of my projects so many serial prints that I commented out because I fixed that part of the code. I don't need it anymore, but I'm going to leave it just in case I break it again later. Not so much in the Arduino. When I worked more with the little basic chips, the basic Stamp 2 or the pickaxe, the serial outputs put more of a strain on them processor-wise. So you want to use those sparingly and get rid of them when you're done. But with the Arduino, one of the things I like to do is I'll crank the serial port up to 115K, so your messages are short, fast, they spit out, and then you're still using them sparingly, but leaving them in has much less of an impact on your code in the Arduino than they did previously in some of the less esoteric development environments. I was going to say one other, let's see, let me jump to I've got an LM35 temperature sensor here, which is that one, which is the third input, which is A0. And we're going to do a little bit of hand waving like we were talking about the 3.3 maximum output. It is a analog temperature sensor. And here we know basically, I'll turn off the auto scroll. We know basically nothing other than the raw value is 158, 160, and that's scaling on the map as it is to 40. But the interesting thing about this sensor is that it puts out 10 millivolts per degree F. So if we will convert, again, I'm going to break the
What sensor are you using on this one?
LM34. That I change it to a 50 for 5 volts. So full scale 5 volts would be, oh, sorry. I need that to be a 500. Let's go ahead just for good measure and make it 5,000. And what I'm doing is I'm saying I want to see real voltage on the output of the output value. So 1023 maps to 5,000 millivolts, assuming I've got exactly 5.000 volts on my input. So when we look here, what we should see is the actual temperature in Fahrenheit. And at a decimal place, 76.7, and it's going up, up, up. Other hand's warmer. And
How linear is that sensor?
vary. Plus or minus, I think over its operating range, like 0 to 70C, it's supposed, well, I bought the cheap ones.
Not the mil spec ones.
The mil spec ones are plus or minus 0.4 degrees Fahrenheit over their operating range. But one of the things I wanted to demonstrate here is, even though we're using a 1024 input, so we're getting 10 bits, but if you look, there's a jump. Okay, that changed by 5 counts, that changed by 5 counts, that changed by 5 counts. So even though it looks like we're getting all of this information, we're not, because this is actually outputting 806 millivolts or 811, somewhere between 811 and 806 millivolts. But our granularity with the 5-volt reference is that 4.88 millivolts. But we can address that by going in here to our setup and add analog reference. Is it 1F or 2? Nope. Can't see my cursor. Turn blue. Now, when we run it, oh, sorry, gotta make one more code change. It's not going to make sense here. What this was for, this line was to map our analog to digital converter full scale to the voltage reference. So I just changed the voltage reference to internal, which is 1.1 volts or 1100 millivolts. So I'm going to map it to 1100 millivolts. Upload it to the board.
Now, I wrote a standard deviation method in that ultrasonic sensor code that I wrote. So you can, and you can change the size of the buffers. So you can buffer like 3 readings in a row and then give yourself an average. So, and then that buffer keeps moving right down the timeline with your code.
And there it is moving. And even though the numbers look similar, when I turn off the auto scroll, you can see that we're getting jumps of, okay, that was probably noise, me wiggling it around in the socket. But if you look up, we're jumping, let's see, 2518. Well, let's see what it looks like when it's cooling off. Let me heat it up for a second and see how smooth it is when it's cooling off. But averaging is one of the things that I didn't hit on that you can use with, for a second. One of the reasons that that a lot of people like analog sensors is you can do low pass filtering. That it's really hard to smooth a digital signal out there where you can lay your hands on it. That you can add a resistor and a capacitor. When we get to the drawing board, we can do that if you want. But you can add a resistor and a capacitor to act as a smoothing filter or low pass filter to smooth out your data when you're seeing glitches. But here you can see we do see increments as small as 1 and still jumping up. But the theoretical resolution with the 1.1 volt reference on 10 digits, I believe, is 1.074 millivolts, which gets us very close to one. The sensor has an output of 10 millivolts per degree. So we're almost 1 millivolt per bit. So we're almost down to 1/10 of a degree resolution. And if you would do some averaging, that would get you in the neighborhood of being able to get 1/10 of a degree resolution out of this. And most of the people who would care about that level are doing sous vide cooking heaters, or they're doing fermentation, or they're doing, you know, other precise temperature stuff. But you can buy, these sensors aren't cheap. I say I bought the cheap ones because I probably paid $3 or $4 a piece for them. But you can do temperature sensing, differential temperature sensing. This is the only time I've ever used the 1.1 volt input. Well, this and using a standard silicone rectifier diode as a temperature sensor.
And you're just lucky that the temperature you're measuring is under 110
110
degrees or
degrees.
something.
This would cap out at 110 degrees. So if your application expects to see over that, then you wouldn't use
You have to use
this.
a different reference voltage.
You'd have to use a different reference voltage. In that case, you could actually use a reference voltage that corresponds to whatever you want. I believe these sensors go up to a maximum spec of 257 degrees Fahrenheit, which is 125 C. Or you could switch to a centigrade sensor, which does the exact same thing. At this temperature, it would be putting out, what's that, 270 something millivolts, 280 something millivolts, 27 C, 26 C, whatever. And those could stay all the way up to 110 C. Unlikely to be seen in this environment.
So when you said whether you wanted to put a low-pass filter on the analog side outside the chip versus averaging or reducing your sample rate or something in the code?
It really depends on what you're trying to get rid of. The low-pass filters, the beauty of those, they work great when you're getting small duration.
Get rid of that 813, right? In the middle of those 807s.
Rather than just smoothing it out?
Probably. I doubt that would get rid of it. Well, I don't know, because I suspect that that's more an artifact of something I've got going on the board, because I don't believe this sensor is actually shifting its output by
I don't think it is either.
7 millivolts.
You get something going on with this jumping. It's 813, 806, go up 813, 806.
Could be RF radiation for that.
About every fifth or eighth reading we're jumping.
Yeah, well, I noticed that there seemed to be some periodicity to those 813s, which made me suspicious. But it's a tale on when you do something in software versus when you do it in hardware.
And what your background is. If you're an electrical engineer, you know how to hook up little RC circuits.
And the
If
software
you're a software
guys-
guy, you know how to average 5 numbers.
It's funny. I did a project for Board Warner Cooling Systems. I was building interface modules for testing the 24-volt electrical system cooling fans. They needed something that would let them do pulse width modulation of a 24-volt signal at 5 or 10 amps. And so I built them a bunch of modules, and they said, yeah, we're reading a TAC input signal that varies between this. Would you like me to throw an input on there for that? Sure. So it was in one module, it was voltage optical isolation, both directions, high current pulse modulation. And they said, yeah, we're having these glitches. Yeah, it's giving us this random reading on our TAC input, and I'm like panicked. And I'm walking them through following the signal back over the phone with the oscilloscope. And then the guy finally says, no, it looks the same on the scope before your box than it does after. It looks the same on both sides. And I'm like, whoa, okay. I don't know what we can do about this, because it turns out that I always had the problem. It just didn't go away miraculously when they stuck my box in there. They've actually been chasing it for 2 years. And this was out in western North Carolina. Well, one of our field engineers from there went through the plant, and he was giving me his report on the phone, and he said, yeah, I was there. Yeah, I'm here watching it, and yeah, I can see the signal come up on the TAC signal come up on the screen. I can see it coming up. I said, you mean you can see the leading edge? No, it's kind of ramping up the screen. Okay, you're sure it's not a leading edge, it's a ramp. You can see it ramping. It's like, okay, we've got an answer. A lot of TTL inputs cannot handle noise on their inputs. And if you have a slow moving signal, what happens is when you get to that threshold where it says, I'm a 1, I'm a 0, I'm a 1, I'm a 0. If there's noise on it, you get glitching because you'll get multiple transitions. Well, I was already using an opto-isolator for the signal conditioning going in, so I talked to their lead engineer and I said, tell you what, I can lay my hands on some Schmidt triggers which have hysteresis, which means they go solidly from a 1 to a 0, and they won't backtrack without a minimum excursion, usually 0.4 volts or something. So long story short, bought some Schmidt triggers, built them 3, sent them to him. He said they work. I said they work great. I said fantastic. Send them back to me. He said I need 18 more of them. And I said, well, send those back to me and I'll build you 18 more. And he said, no way in hell. These are not leaving our test bench. He said we got the only test bench in the country that can measure these units. So I built him 18 more units and shipped him some and sent some up to Marshall, Michigan. Still couldn't get my prototypes back. I finally told him, tell you what, I'll sell you the replacements at half price, but I won't ship them until you send my prototypes back. And that's what I had to do, but I finally got my hand-wired rat's nest prototypes back.
Right. So that
but-
you get them then and not 2 years later.
Or ever.
Right.
That what I didn't want to have is have it fail after being on a test bench and my rat's nest wiring fall out, and then someone say, look at this thing that failed in the field.
Right.
Been there, got a t-shirt. But the story was the software guys for 2 years had been trying to filter out those glitches in software.
They couldn't do it.
The software guy in me tells me, I think I could have done it. But what you had to do is predict what the frequency actually was and build a window to ignore any glitches that fell out of your modeled response of the system. And what they were trying to do was more low passing, more averaging, and couldn't get it out of the system. So there's times hardware is the fix and there's times that software is the fix. Lots of times, I just did a system in my wife's car that I've built something in the car now that when you turn the key off, you've got 7 seconds. If you twiddle the key once in that 7 seconds, all the power outlets and the DVD players stay on for 90 minutes, and the GPS stays on for 90 minutes. That I was having trouble because it will stay on for 90 minutes or until the battery voltage drops below 12.3 volts. I was having some trouble because as you're opening and closing doors and turning fans on and off, that occasionally I would get little glitches, little excursions below the 12.3 threshold. So I just stuck something in there to take the 10-point average and just add them up. It was simple code, very brute force. There's nothing elegant about it, but you're taking, more or less what I was doing was taking a sample, using it as my starting point. Next sample, shoot, I can't even remember if I added it and divided by 10 or if I divided it by 10 and then added it and kept a running average. But it was, they take 10 points and add it up. And signals that are actually fluctuating, that you have actual noise on. The averaging is a great way to do it. You can actually increase your resolution. It's a point of diminishing returns. There's a curve that flattens out at the top. The more samples you get, the more accuracy that you get from it. It's like there's a constant bandwidth product or something. That taking 10 samples provides a big increase in resolution versus 1. Taking 20 doesn't provide nearly the benefit that taking the first 10 did, and by the time you're up to 50 samples, it's really point of diminishing returns. You're not getting much back, but you're still, because you're slowing your system response down so much that you're not getting much resolution for it. I think that's most of what I had to show and talk about. Any other questions? Sensors? And again, I'll try to send a link to Peter or send an email out that will have a link to the slides, and then some notes I have with links of places like a link to where you can go and sign up for the Omega books if you want to get the entire series of books. I think you can also sign up just for the Sensors or just for the New Horizons, which is their coming attractions book. Yes, sir.
If you send me the files, like the slides, we can put them on the web page. And put
They
them.
only exist in the cloud as far as I know, so I can send you the
If
link
they're-
to them.
If they're on the cloud and they'll stay there,
Yeah,
then we can link to them.
I think so. I've never done it, but
There's a size limit on the email messages to the list. And so
yeah, I think
it's
just send the
better.
link. That way people who don't care
Yeah.
aren't burdened with that
Sure.
package.
So my kids want to be able to make temperature sensors to monitor this big cage with a huge python in it.
Uh-huh.
All we need to do is the Arduino. I don't need to connect it to the Raspberry Pi unless we want to collect data to say, how is the temperature varied over the last
You can
3
do that
weeks?
on the Arduino also.
Well, I would recommend probably going with the Pi if you could.
Why?
Because the Pi has access to Python and hosting a web page, and there's a whole set of connectivity skills.
Yeah, that's true.
That
Okay.
the Raspberry Pi has at its fingertips if you have those skills. And I think developing those skills will be more important to your target audience, and they'll pick it up faster than I would. And you can do it on the Arduino, but it's an add-on layer. That's not what the Arduino is designed for. The Raspberry Pi, that's another notch up, where I feel like the Arduino is a much better rapid prototyping I want to do a proof of concept kind of platform.
Okay. So, as far as signal timing, I've seen some stuff on interrupts. Have you done much stuff on interrupts? or have-
Love interrupts.
Okay, 'cause
Absolutely love them.
I got the basic interrupts where, rising, falling, stuff like that.
Mhm.
But there's.
Yeah, the clock timers, that's
On
another
clock
level.
timing on the whole interrupt, if you had a link or had some
I've got-
reference stuff on that, I would love to know, because I know when my interrupts will sort of come in and the timing my interrupts, so I don't need to constantly mess up my code with the.
I had to do an interlock. Someone asked me to do an interlock for a water-cooled laser that, to make sure that the paddle wheel was turning to indicate that there's flow going on, that the laser is being cooled. And I did the entire project just in interrupts. The main loop in the Arduino is completely empty. That there's just nothing in it. That it waits to see so many paddle wheel turns, it times out, it uses interrupts on the inputs for seeing that the Hall, actually I don't think it's a Hall effect switch, I think it's a reed switch with a magnet. And then it uses the timer interrupts and changes those to time what the pulses, how fast the pulses are going. They have to be spaced at least so close together. And then if they go so far apart, it turns the output off. And again, all done with interrupts. Can't say it's good code, but I was very proud that it worked.
That's what I need to see, because there's, I have the interrupt just kind of always just violating coming in and out of my Arduino, and then I have two sets of interrupts coming in and out of my Arduino, and then I'm like thinking to myself, how many of those collided in each other? And, there's code where you can actually specifically say to look for those interrupts.
My understanding, the holy grail is do the absolute bare minimum that you can while you're in an interrupt. That you don't want to be sorting lists or doing any big math calculations while you're in the interrupt. If you can keep the footprint as small as possible, then there's enough clock spacing that you're not impacting other things. And that also depends on which timers you're using. I know another reason I like the timers for pulse width modulation 8, 9, and 10, that for some reason that they seem to get stepped on less by the timer use in the Arduino. But I can shoot you a link.
Because you saw my project, you saw my project.
Yeah.
And so I always had that question of, am I actually timing each one of the bikes correctly, or is one getting stepped on a little more than the other one?
Well, when you're talking about human interaction, pedaling something, I believe you would be very hard pressed to, as long as you were doing edge interrupts.
Yeah.
So once the edge went away, the interrupt was done, that with human interaction, I think you'd have a hard time generating enough interrupt frequency that the Arduino would have any trouble with it.
726 milliseconds.
That was the period?
Yeah.
Okay,
that's how often it is.
Oh, that's slow.
Yeah, so.
Yeah, that's eons.
Compared to 8 megahertz, it's very slow.
Well, you're using 8 megahertz CPU?
Whatever the.
Uno's 16 megahertz. So that's 16 instructions every millionth of a second.
Yes.
So 760, take one of those, and that's a millisecond. Then 1,000 microseconds in that. And each one of those microseconds, it did 16 instructions. So it's lots of instructions. You would be much more likely to get in trouble if you're trying to do collecting data points and doing averages and then calculating new outputs.
I do that outside. I just pass the number back.
Then no, I doubt that you would have any trouble with your.
Compare it to compare the duty cycle to the main clock, subtract the difference, send it out.
Okay.
That's all I do.
It sounds like you're. But if you'd like me to look at the code, I'd love to see if there's any way I can
because I'd love to
help.
get a little more, because I've seen people who do that type of stuff and then they change, what it's doing and what it actually was. Because I have some other applications.
I love pretty code. I hate clever code. I can't.
Well, mine's kind of a sledgehammer. So.
Oh, that's what I like. I like it that I was reading some code I did for. I mentioned the processor hula in the email I'd sent out. I did a processor leveling system for an X-ray film processor. And one of the problems that they told me out in the field, it's like, no, I'm parking pretty level. I think it should be leveled, but the thing is like moving around. And I said, it's not leveling. Well, no, it is leveling, but it's doing some other stuff first. And I could not figure it out until I finally studied the data sheet. And one of the questions, one of the pieces of information I had ignored was it said bandwidth, 0.25 hertz. Well, what do I care? I'm not high-speed sampling. I finally understood 0.25 hertz. Wait a second, that's 4 seconds. That means when you turn it on, your data is not valid for 4 seconds. So I have to put a delay in there to wait for it, because otherwise I started responding to the invalid data and changing the leveling, and so it would do this little hula dance and then it'd level back up, and I liked it because I could tell it was doing something. What was funny is nobody liked it when I put the timer in, because they'd turn it on and then it just sat there for 6 seconds. It's like, did it come on or did it not come on? And then flip the switch again, so I actually had to add a beeper to count down to let it know. It's like, I'm waiting for it to warm up, I'm waiting for it to warm up. And that smoothed it right out, but it was something I missed in the data sheet. But when I was reading through the old code, I felt like I was reading, you know, a love letter to my project. That here in this section, we're collecting these values and these values, and this is what we're watching out for. Be wary of this. One of the notes I saw was I was using EEPROM. What I would do is I'd use a manual box with switch levers and level it exactly how I wanted it. And I actually wanted to cheat a little tilted back because the overflows were at the back. So if it was going to overflow a little bit, I wanted it to be tilted a little too far back than too far forward. So I'd set it, hit a button, it'd store the EEPROM values, and that's where it would come back to. Well, I had forgotten in 10-year-old code that, but there was a note there that says, caution, EEPROM values are corrupted during programming, must be recalibrated upon programming. So I knew not to have the leveling system up and running, because as soon as I program, it's going to go, because it goes back to just whatever random comes up in the EEPROM. So I love boring, well-commented, verbose code. I hate the cute little, oh, I can fit these 17 C functions in one line if I use this bracket and this bar and this ampersand with this and a couple of carets. And it's like, I have no idea what you're doing.
Well, that's fine until it won't fit.
Oh, well, I catch myself making code more and more compact or stacking on a line. I like printouts to fit on one page.
Yeah, nowadays memory is so
free.
expensive. Yeah.
So the other question for the group, has anybody ordered any, there's a new thing, and I saw it over at the Maker Faire, where they have addressable LED strings. I don't know if you guys have seen this. It's 2-meter long strings, and each one is singly addressable, brightness, the whole bit.
I think Adafruit has some stuff like that.
And I was wondering if anybody wanted to buy some of those in bulk, because I'm thinking about putting some waterproof orders into China, and you can get the stuff for like
Cheap.
$8 for 2 meters or something like that, so you can do your own.
Be careful that you see 50/50 LEDs and not 35/28 LEDs. Because as long as it says addressable, you'll be fine. I just sent back a spool that, well, it wasn't working right, but I bought a strip of RGB LEDs that was the 35/28s, and it turns out that that was a strip of red LEDs, blue LEDs, and green LEDs, and then blue LEDs and red LEDs and green LEDs. But it says RGB strip LEDs, so they weren't individual. This is actually an addressable collection from Adafruit that I put together for a demo for a trade show that uses a rechargeable battery pack. I've salvaged the processor. It's got the screw holes for the processor. I laser cut it over at the tech shop, but I did the bending using an acrylic bender that I built out of a piece of aluminum strap and a piece of leftover flooring and some 26 gauge nichrome. Worked nifty. It was so cool watching the nichrome heat up and cool, but I thought it was neat to be able to bend it, so that's what I actually bought it.
So you soften it with the nichrome and then just
Yep.
punch it over?
Yeah, I turned this up to 2.1 amps, I think, which is 800 degrees C. You lay it there for so long, and then you just bend it gently. I had some junk pieces that I practiced bending and unbending and straightening with it, but not my design. Google's your friend. I found enough dissimilar pieces that put it together with the Tripped Ace hardware. I had an acrylic bender.
And why didn't you use the one at Tech Shop upstairs?
I didn't know enough about it. I don't know if you had to sign off on it or not, but at that point I'd gotten the bug and found that I could build one. So I have enough nichrome to build tons of them now.
Is that open or is that closed?
But when you did the laser cutting there, so
Nice.
they also had acrylic strip you.
I never used the acrylic strip stuff or the
I used it
vacuum
once
forming.
making work, but that's probably because I didn't exactly know what I was doing.
Was there a neat trick that Mr. McDougal wanted you to?
Oh, yes, yes. I was trying to figure my way back to see if it let me do the .cam. I see color things here. Will it let me do stuff with my finger? How do you do the color marker things?
You're not really supposed to color on that, I don't think.
Whiteboard.
There's a whiteboard
Oh,
right behind you.
hey! Marker things.
Go low tech, is that it?
Where's the on button?
Assist.
Uh,
Yeah, be careful for that. Don't mess up that soda pop equation.
Yeah, really.
What the hell is that?
what
Carbon
you do is-
dioxide.
Oh,
You can
carbon
look-
dioxide and water, yeah.
It's a reversible reaction.
And what you would have is, I can't remember if they may have had the gate tied directly to the VN. But what happens is, and this has a first bias body diode. So what happens
Is
is,
that an N or a P?
in type.
Okay.
Sorry.
On the low side.
So you've got, when you pull the gate up, use a logic level FET. Most of the logic level FETs will tolerate 15 volts on their gate anyway. I've never seen any say that they need protection at anything below 15 volts. So what happens is when you hook up, say you hook up 12 volts here, ground here, this pulls up the gate, this turns on, this will have a very low voltage drop. I mean, I can't think of what FET that they used, but it's I mean, definitely sub-ohm. I mean, you can get FETs down in the milliohm now for the big FETs. But you would only need something that was rated to have, I mean, I would think that the benchmark is just putting a diode in series with it, and you're losing 0.6 volts for a silicon diode and what, 0.2, 0.3 for a Schottky.
Yeah.
So this gets you, well, your figure of merit is below 2 millivolts, 200 millivolts drop. But the nice thing is, if you hook the voltage up backwards, this thing will also have some large value of resistor here, probably a meg, just so that static can't charge the gate up and let it turn on. So when it's unplugged, laying there in the box, and you hook it up, the gate is pulled low, you hook it up backwards, that the gate is high and the device isn't powered. When you hook it up like this, does that sound right? Or my, something feels
So
backwards.
when it's backwards, the gate is grounded, right? And
Let's see.
and it won't turn on until you pull the gate up to its input voltage, which
Let me see if I can pull up Pololu and it's gone now. There's Pololu. I'm trying to think of one of their things that used the, seemed to be, it was always their motor controllers. I can find it and send a link. It could be a PFET. See, it's on the low side, which makes it an InFET.
Well, yeah,
I don't think it'd be an
when it's powered correctly, the path through that resistor,
This is probably 10K or something.
Paul was talking about it, pulling it high. I was just gonna point out that, I mean, the diode is going
Okay,
to
that's it.
block.
That's
It's going to block the,
That's it. It's hooked up upside down. Because you have to draw the body diode first. Because you want the body diode to conduct in this direction. So if you left it with just the body diode connected, you'd have your 0.6 voltage drop. But
you want to short it.
So put this diode out here. So what you want is it's reverse connected, but the the FET does not care whether you pull the drain or the source, whether you're referencing the drain or the source when you're using the gate voltage. It turns on either way. So what happens is, there we go. I was struggling because when you hooked up the reverse direction the other way, the body diode was forward conducting. So this way, when you hook it up, even if it doesn't turn on, the body diode turns on. So when you hook the voltage up normally, the body diode is on, 0.6 volt drop on it, but the FET turns on 0 voltage drop over the signal. But when you reverse bias it by hooking the power up backwards, the body diode is reverse biased, so it doesn't do anything for you. And the FET gate is actually pulled below
To ground.
It's pulled to ground, and which is below what you're going to be seeing on the drain. I think that's right. Yeah, that's the drain. So by sticking a small MOSFET onto, sticking a 20-cent MOSFET on top of a $50 motor controller, that instead of all the smoke coming rushing out when you hook it up backwards, it just sits there and does nothing. You flip the power around and it comes back on, and you don't get a voltage drop like you would with a normal diode. And the thing is, you can make the FET as big as you want. So I know you can get SO8 FETs rated for, in their applications, that they have SO8 FETs. I know 15 amp applications. And you generally, figure of merit I've always used is you can count on 1.5 to 2 watts of dissipation for a non-heat sink mounted FET. So I've got a little calculator for the RDS current and stick it in a watt or 2 watts. Any other questions?
So if I want to measure my
Battery voltage?
battery voltage, if 1023 is VCC, as VCC falls, it's still going to say 1023.
That's when you go to the internal VREF at 1.1. And you can use a voltage
Use the
divider on your
divider,
external,
Use the internal VREF.
which won't start dropping until you're crashing.
Okay.
Yeah, so what I do is I have a battery coming in.
And if you've got a battery and a voltage regulator, then you can measure, you've got 5 volts, right? And you can measure your 9 volts with a voltage divider.
That's
And
what
so
I'm talking
that works fine, but when
When you're using
When
the
you don't
battery to
have-
power the thing you're
yeah,
measuring.
when you don't have a voltage regulator,
You have to use
VCC
some other
falls
reference.
down and the VREF falls down and you're constantly reading full power, 1023.
Well, there's a couple things that you can do to hand wave.
You could use the external reference and make yourself a divider.
Another battery?
No, the external reference.
No,
The external reference pin on the Arduino. Well, you're doing this on a Tiny, correct?
Yeah.
Tiny doesn't have an external reference, but what you can do is you can fudge your own.
That doesn't help you.
You want to use the internal reference.
Yeah.
You want to use a voltage divider, but the other thing you want to do is you don't want to drain your battery with a voltage divider out there on all the time, so you want to use an InFET to turn on the voltage divider. So you've got your upper resistor, and then the center, you want to protect it going to your processor with a FET as well. And then the lower resistor, but instead of that connected to ground with a complete continuous drain on your battery, you put another InFET down at the base, which then you apply voltage to both those FETs. That gets you your connection and your voltage divider to bring it down, and you use your internal reference as your reference.
But just wait until you turn on that voltage and sample the battery like once a minute or something.
Yeah.
but if you didn't care about the current draw, you would just make a voltage divider and use the internal 1.1 reference.
Does the AT Tiny have an internal 1.1?
I'll look up in the data sheet.
Actually, that
You can
That's good.
fudge your own if you'll take an extra output pin and put a 1K diode and a silicone rectifier and use that as your voltage reference. When you're driving that around 5 volts, you should see 4 point something milliamps. You should measure about 600 millivolts across the diode. So as your voltage drops and your analog to digital converter reference starts dropping, that you're still going to measure the same counts, but you know that that's supposed to be 600 millivolts. So you can back calculate and say, this voltage equals 600 millivolts. Now this voltage equals 600 millivolts. Now this voltage equals 600 millivolts. And back calculate using that as an external reference, but you just read it on one of your analog to digital channels and use that to scale the measurements you're taking on the other analog to digital channels. Does that make sense?
So it stays at 600 millivolts
It stays at 600 millivolts.
without
You
regard
know
to
that
the
that's
input
true,
voltage?
but you know that's genuinely 600.
Yes. Yeah, so that stays at, as long as you're running it around that current. It'll vary with temperature, 2 millivolts per degree C, but it should be around 600 millivolts. I was measuring on a 1N4007 last night, 640 millivolts at 81 degrees with a 1K resistor. And you can turn that output on and off, so you're not burning that 4 milliamps for nothing the whole time you're sitting there. You just turn it on when you need a reference value for your A to B calculations.
That's a good idea to use the FETs
How many
to keep
pins
your
do you got?
current draw. at absolute-
-1.
I think I know how to do it with one pin,
Okay.
but I'll talk to you about that later.
Maybe you could multiplex VCC and ground.
Yeah, that's it.
Maybe. Time.
Cool. And the link will have the thing with the PFET with the pulsing to not be draining your battery the whole time with your.
Use big resistors, and there's not much drain.
True. As long as you don't mind the error on your A to D, because it's one of those foot race things. But I've always felt like you
The
can.
thing you gotta be careful of is, your battery will show a higher voltage with no load. So you need to make sure you've loaded your battery when you're measuring. Now, if your system is operating, it will be under load and you'll get a reasonable value. But a lot of people who are doing handheld devices and they're doing stuff on a timing basis, and then they go out and they measure the battery and it's showing them, oh, I've got a AA battery at 1.5 volts, it's a brand new battery, and they don't realize all of a sudden they put a load and the thing swings down to 0.9 volts and basically dead.
There's
You know, that's why you need to have a load on your battery when you measure it. But that's why you want to put the NFET so that you can cut that load off after you've done measuring.
He's got some cool wireless modules up and running that he's had running off a battery for, I think the longest one is like 3 years. And they do a measurement right before they transmit, and then they do a measurement right after they transmit, and then at the next transmission it transmits the before and after, so you can actually see how the voltage drops for the battery transmission. But this is how how do you measure the battery voltage over a period of time of 10 years, or not 10 years, 3 years without draining it. And you can see
Now
here.
that's showing a PFET there.
Yes,
The
on the
thing
high
you gotta
side.
be careful also, a lot of people make this mistake, they're used to NFETs. In an NFET, the source is at the lowest voltage. In a PFET, the source is at the highest voltage. So it's, you know, complete mirror. A lot of people have a tendency on a PFET that they hook the drain to the highest voltage, just like you do on an NFET.
You know, which ones he got hooked up there. Sits the drain. But anyway, it's showing here that when he pulsed it, it stayed in the on state for 21 milliseconds. Or the Arduino can sample, I believe, it up to 10 kilohertz. And here's one. They switched it to a different pull-up. There's 202 microseconds. What's this next one down here? Showing how it changed as while they varied the voltage across the battery, so that you could tell when he pulsed the pin at low voltages, the PFET stayed turned on for longer. So I think it's just saying that as the gate voltage drained off of the PFET gate, at a high voltage, it drained off fast enough that the FET came out of saturation. But at such a low voltage across the FET, the charge on the capacitor stayed up long enough to keep the FET in saturation longer. But he's got some really cool stuff.
Post that link.
Yeah, that's one of the things that I came across. It's like, oh yeah, this is going to be cool with the sensors
Yeah.
that and G-Labs. They're actually sold in the U.S. through Modern Devices, which they've got a cool blog and cool stuff too. Oh, page up. That was nifty. Again, I had to read both parts of it 3 times before I felt like I could wrap my mind around it and knew what they were talking about.
Looks like this was done in Europe.
Yes, he is in Europe, and it was posted it back in May, so it's relatively recent. But he's got some really cool things. They're talking about doing the continuous operation of the wireless units and doing the transmissions.
I can tell by this type of resistors.
Oh,
When I lived in Brazil, I did the same thing in Brazil. They used
the boxes
they
instead of
used the
squiggles.
boxes instead of the,
The squiggles.
yeah.
Okay, great.